Hi, myself Susobhan Bandopadhyay from Bhubaneswar. I will be presenting our work parameterized algorithm for finding highly connected solution. And this is a joint work with Ankit, Abhinav and Aritra Banik from Bhubaneswar and Saket Saurabh from IMSC Chennai. So let us first start with the problem definition and motivation behind starting the problem. So given a graph G on n vertices, two integer k and l. The problem asks whether there exists a solution to the problem S of size at most L such that G induced on S is n minus k edge connected. That is, any two vertex in G induced on S share n minus k edge disjoint paths. Lewis and Yanagaki showed that most of the vertex relation problems are NP complete. Not only that, some variants are also NP complete. Recently, Anderson studied lambda edge connected vertex cover uh, and gave an algorithm with running time to the power order of lambda L multiplied by n to the power order of 1. Basically, the problem asks whether there exists a solution of size L such that it induces an lambda edge connected graph. So for our case, the lambda is n minus k, and substituting lambda L with n minus k, we get n minus k all square. So this is exponential time algorithm we are getting. So this algorithm won't work for our problem. But while starting the problem, we prove that if n is greater than 2k and the graph is n minus k edge connected if and only if for every vertex in the graph has degree at least n minus k, where n is the number of vertices in the graph. So this is pretty clear that the solution must contain at least n minus k plus 1 many vertices, and it excludes at most k minus 1 many vertices from the entire vertex set. So in n to the power order of k times, we can guess the set of vertices that are not part of the solution. So we are getting XP algorithm for vertex subset problem like vertex cover, FVS, cluster vertex relation, planar vertex relation version. For all this problem, and it's a highly connected version, a highly connected dominating set as well, whether given a graph and integers k and l, we want to find a solution S such that every other vertex in the remaining graph is adjacent to at least one of the vertex in S, and G induced on S is n minus k is connected. Similarly, for highly connected multiply cart ask that given a graph on n vertices to integer k and l, an additional set of vertices T, it asks to separate all the vertices after deleting a set of vertices S. That is, we want to remove a set of vertices S such that in the remaining graph, no two vertices from T are connected via path. And obviously, the additional constraint is G induced on S is n minus k is connected. For highly connected multiply cart, we want to find a subset S such that whose removal disconnects every given pair SITI in the remaining graph. And again, G induced on S is N minus K edge connected. So now we know that all these problems are XP, but the big question is whether they are FPT parameterized by K. Let us first tell what we got. That is, we proved that highly connected vertex cover and highly connected feedback vertex set are FPT parameterized by K. Highly connected F deletion problem is parameterized by FPT parameterized by K. Highly connected Steiner subgraph problem is FPT parameterized by K. Highly connected dominating set and multi-way cart are also FPT parameterized by K. So for solving these two problems, we have used highly connected Steiner graph as one of the key tools. In fact, for highly connected dominating set, uh, highly connected, if we have solution to highly connected Steiner graph, then we can do some small tweak and we can solve a highly connected dominating set. Lastly, we have shown that highly connected multi-cut is W1 hard parameterized by K, and we have proved this by giving a reduction from independent set. In this talk, we will talk about the highly connected vertex cover and highly connected Steiner subgraph. Uh, so let's first get hold of this problem by solving highly connected vertex cover. And this is the definition of the highly connected vertex cover given a graph G on n vertices to integer K and L. Highly connected vertex cover ask whether there exists a vertex cover S of size at most L such that G induced on S is N minus K edge connected. So clearly from the previous theorem we have proved, we can easily say that uh, the graph induced on, if the graph induced on S is N minus K edge connected, then every vertex has degree at least N minus K. So those vertices which have degree less than N minus K are of no use for our case. So we will consider only those vertices which have degree at least N minus K. So we will call that set of vertices as VH. Now we will break our algorithm into two cases. When the cardinality of VH is exactly N minus K plus 1, then we have to do not more things. So basically we will check whether the graph induced on VH is N minus K edge connected and this is forming a vertex cover. If this is no, then we will say no instance, otherwise we will say yes. So let's now concentrate on the other case when the cardinality of VH is greater than N minus K plus 1. So in this case, we can guess that whether there exists a vertex V which is outside the solution. And as we are solving the vertex cover problem, so if V is not in the solution, then all the neighbors must be in the solution. And as V has degree at least N minus K, so we have already included N minus K many vertices into a solution. So we are only left with K many vertices. So we want to find a subset X of VH minus neighborhood of V such that X along with neighborhood of V forms an highly connected vertex cover, and clearly there are some 2 to the power K many choices for X. So we can solve this problem in a bit time. Now let us go to the Steiner subgraph problem where we're given a graph with n vertices, a set of terminals T to integers k and L. The problem asks whether there is a subset of vertices of size at most L such that it contains T and induces a graph which is n minus k edge connected. So if let us consider V is one of the vertices which has a degree less than n minus k, so we will denote that as VL. So V belongs to VL. So if k is less than 1, less than or equals to 1, that means we are looking for n minus 1 connected solution. So every vertex has to be in the solution, but here V is one vertex which doesn't have degree n minus k. So this is no instance. And the other way, when V belongs to T and V belongs to VL as well, so we know that V cannot be part of the solution. So that is also no instance for our problem. So in the remaining case, we will delete V from our graph and we'll make k equals to k minus 1 and reduce the instance. So this is not very hard to see the reduction rule is safe. I am not going into the proof of this reduction rule, but after exhaustive application of this reduction rule, we know that there is no low degree vertices left in the graph. So VL is now empty set. Now we divide VH into two parts so that V1H and V2H. So V1H is the set of vertices which has degree in between n minus k and n minus k plus VH minus L. So basically VH minus and V2H is the set of vertices which has degree at least n minus k plus VH minus L. Now we will try to bound the number of vertices in V2H. So let us fix some notations. We will call VH minus S equals to VH minus S to this part, and A star be the set of vertices which are neighbor to all the vertices in VH minus S. So basically A star and VH minus S, they are forming a complete bipartite graph. And we know that A star, as A star is part of solution, so A star has at least degree n minus k inside the solution, and as the coordinate of VH minus S is VH minus L, so it has VH minus L when neighbor outside, so it has total degree n minus k plus VH minus L. So total non-neighbors of VH minus L S in S is at most k square, because the number of vertices here is bounded by k and number of non-neighbors of those vertices are also bounded by k. So we have total non-neighbors of k square. And as we have already shown that A star is a subset of V2H, so coordinate of V2H is greater than or equals to coordinate of A star, which is L minus k square. So this is greater than or equals to n minus k square. From this, we have the following corollary that V1H is bounded by coordinate of V1H is bounded by k square plus k, so which is some f of k Depending based on this corollary, we are trying to solve one problem with some additional information that is called a annotated Steiner subgraph problem, where we're given a graph with minimum degree n minus k, two sets t, which is terminal, and the other one is x, that is a subset of uh, vertices in the graph G, two integers k l. We want to find a subset S of size exactly L such that S contains T and S contains X from V1H. And obviously G induced on X is N minus KH connected. Now let us say that we can solve this problem in some FPT time. Then can we solve the original version in some FPT time? Yes, because here we are guessing X, which is we're guessing the set of vertices from V1H, which are the part of the solution. And we know that coordinate of V1H is some order k square. So k square choose some k. So we have some 2 to the power big O of k log k many choices for x, and we can solve the problem in some a prime of k time. So now let's concentrate on annotated version of this problem and solve this problem. So before going into the solving part, let us define the realizable subset. So for a given set X and a subset Y of X, if there exists one vertex V in V2H such that neighborhood of V in X is exactly Y, then we will say that Y is realizable with respect to X. So let us assume that X1 through Xi be the set of all realizable subsets of X, and Hix be the vertices in V2H such that uh, which has neighbor in X exactly equal to Xi. Now we prove the following exchange lemma. Let us there exist two vertices U and V in Hi of X, but one in the solution, the other isn't. Then we can basically include the other one, and exclude the one which was previously in the solution, and we get a new solution. Let us see the proof. Let us denote SV as the new potential solution, which is S union V, and we are excluding U. And we know that for any W which was in the solution and which was the part of V2H, as they have degree n minus k inside the solution, because there are at most VH minus L many vertices outside the solution, and these vertices have degree n minus k plus VH minus L. So from here we can the figure we can see that U and V sees the same neighbor in V1H intersection S, so their degree is also same. Again, for any other vertex inside this gray part, that is v1h intersection sb, they have degree n minus k, because by including that vertex v and excluding that vertex u, we're not going to change, we're not changing degree of any other vertices. Now it is not very difficult to see that number of realizable subset uh, is order of k cube, because the cardinality of v1h is bounded by k square, and there can be at most k many non-neighbors for each vertex. So the realizable subset is order of k cube, and for each hix we can guess how many vertices are not part of my solution. After guessing all the bi's, we have the vector b1 through b psi, and as we have bounded psi by k cube, so first what we will do, we will basically guess from which are contributing in this total vector. So that is by choosing, there can be at most k many vertices outside, so there can be k position where we have non-negative values or values greater than 0. So by choosing k cube, choose k, which is 2 to the power k log k, we can guess the position where we are having positive values, and the values can be guessed using by some multiplied by 2 to the power k. So in, so basically we have total legal vectors of size 2 to the power uh, order of k log k many. So now we have the solution for the annotated highly connected Steiner subgraph problem, and we can solve the problem in to the power big O of k log k multiplied some order of 1 time, and recall the previous lemma which says that if annotated version of this the problem can be solved in some polynomial time, fpt time, and then general version of this problem also can be solved in some fpt time. So using this two lemma, we have the following theorem that says highly connected Steiner subgraph also can be solved in fpt time. So let's summarize our talk by uh, giving an overview of this talk. That is, here we have designed some FPT algorithms for highly connected versions of several natural problems such as vertex cover, feedback vertex head, Steiner subgraph, multi-cut, multi-by-cut. For multi-cut, we have given W1 hardness reduction, and for all those we have used the parameter k, that is the distance from being n minus k edge connected. And one interesting direction to pursue is to like exploring the kernel and uh, the non-existence, by showing the non-existence of the kernel of the problem. So that's it. Thank you.